70% of the universe is a force you cannot see, and right now it's pushing every galaxy apart faster and faster. For 25 years, we assume this force never changes, a fixed number written into the equations of the cosmos. The largest map of the universe ever made just suggests it's fading. If that's true, the rules we thought were permanent aren't, and the way the universe ends flips completely. But a growing number of physicists think the signal might not be real at all. In 1998, two competing teams measured distant exploding stars to figure out how fast the universe's expansion was slowing down. They expected gravity to be pulling everything back together, putting the brakes on. Instead, they found the opposite. The expansion wasn't slowing, it was actually speeding up. Something was pushing the universe apart, overpowering all the gravity of every galaxy combined. We didn't know what it was, so we gave it a name: dark energy. The discovery won the Nobel Prize, and it left us with a force that makes up roughly 70% of everything, and we have almost no idea what it is. The simplest explanation was the cleanest one. Dark energy might be a property of empty space itself, a constant amount of energy in every cubic meter of nothing, the same everywhere for all time. Physicists call this the cosmological constant. Einstein had written exactly this term into his equations decades earlier. This idea became the backbone of the standard model of the universe, called Lambda CDM. In it, dark energy has fixed strength that never changes. For 25 years, every observation fit. The constant held. Then came DESI, the Dark Energy Spectroscopic Instrument. Mounted on a telescope in Arizona, it spent 3 years building the largest three-dimensional map of the universe ever made, charting the positions of nearly 15 million galaxies and quasars stretching back billions of years. DESI measures expansion using a ruler baked into the early universe. In the first moments after the Big Bang, sound waves rippled through the hot plasma and froze into a fixed scale, a preferred distance between galaxies, the same everywhere. Because we know its true size, we can measure how stretched it appears at different distances, and read off how fast the universe was expanding in each moment in cosmic history. When DESI traced that history, the constant cracked. Dark energy did not look fixed. It appeared stronger in the distant past and weaker now, as if the force was pushing the universe apart has been losing strength over billions of years. In its second data release, the DESI Collaboration reported that this evidence had grown stronger, reaching a significance between 2.8 and 4.2 standard deviations, depending on which supernova data was included. One of the lead physicists, Mustafa Ishak Bushaki, said that at 4.2 sigma they were reaching a point of no return. It still hasn't crossed 5 sigma, the gold standard physicists demand before calling something a discovery. But it was no longer a whisper. If dark energy is weakening, the single biggest assumption in cosmology is wrong, and the fate of the entire universe is suddenly back up for grabs. Here's why this matters beyond the equations. The strength of dark energy decides how everything ends. In the standard picture, with a constant dark energy, the expansion accelerates forever. Galaxies race apart until they vanish past each other's horizons. Stars burn out. The universe drifts into cold, empty darkness. A slow heat death astronomers call the Big Freeze. But if dark energy is weakening, that future is no longer guaranteed. A fading force means the acceleration could slow, and if it weakens enough, gravity could eventually regain the upper hand, pulling everything back together. The expansion would reverse, and the universe would collapse. A big crunch, the opposite of the Big Bang. So this isn't an abstract argument about a number in an equation. It's the difference between a universe that ends in ice and one that ends in fire, and we don't yet know which. But before we rewrite the end of the universe, there's a problem. A growing number of physicists think the signal might not be real. DESI's evidence doesn't come from one measurement. It comes from stitching together three very different datasets: the cosmic microwave background from the early universe, exploding stars in the more recent universe, and DESI's own galaxy map in between. The hint of evolving dark energy only appears strongly when you combine them. And that's exactly where the skeptics are pushing. A 2025 analysis by physicist Deng Wang argued that these three datasets are in tension with each other. They don't fully agree. So combining them is problematic, and the claim of evolving dark energy isn't robust. Look at each dataset on its own, and the signal weakens. Others point to something even simpler. In 2026, physicist Slava Turyshev noted that a tiny error in how we calibrate distant supernovae, just 2/100ths of a magnitude, a rounding error by the standard of everyday life, could create the entire disconnect. No new physics required, just a slightly miscalibrated ruler. And a 2026 study by Afroz and Mukherjee made the sharpest point of all. Before you ask whether dark energy is evolving, you have to ask whether the datasets you're combining are even mutually consistent. If they're subtly biased, you can get an answer that's extremely precise and completely wrong. So here's the honest state of it. What's agreed? Dark energy is real. It dominates the universe, and the expansion is accelerating right now. What's fiercely disputed? Whether dark energy is constant or fading, and whether DESI's signal is new physics or a flaw in our instruments. The reason this stays unresolved is the same reason it's exciting. The evidence sits between 3 and 4 sigma, strong enough to take seriously, not strong enough to bet the standard model on. Many promising 3 sigma signals in physics have evaporated with more data. Some have turned into Nobel Prizes. What settles it is more data, and it's already coming. DESI is still mapping. The Euclid Space Telescope and the Vera Rubin Observatory will deliver independent measurements over the next few years. Within this decade, the signal will either climb past 5 sigma and rewrite cosmology, or fade back into the noise. For a century, we built our picture of the cosmos on the idea that its deepest rules were fixed. Dark energy was the most fixed of all, the constant, the unchanging energy of empty space. Now, the largest map of the universe ever made is whispering that the constant might not be constant after all. We don't yet know if we're looking at a new law of nature or a flaw in our own instruments. But the answer decides nothing less than how everything ends, in endless cold or in a final collapse. For now, the force that fills the universe is keeping it secret. If this one was worth your time, a like genuinely helps the channel grow. Subscribe if you want more of these. Thanks for watching. Clear skies.